Hi everyone, we have got a general idea about what are semiconductors and how they are different from insulators and metals. Now we will study about different types of semiconductors. First classification is based on the composition of the semiconductors and can be divided into two categories, namely intrinsic and extrinsic semiconductor. Intrinsic semiconductor are also known as pure semiconductors. These semiconductors have low conductivity. Pure silicon and germanium are common examples. However, the conductivity of these semiconductors can be increased greatly if even a small amount of impurity such as group 13 and group 15 elements are introduced in it. These impure semiconductors are called extrinsic semiconductors. Extrinsic semiconductors are further divided into two types, p-type or n-type. First, we will talk about n-type semiconductor. If the introduced impurity is having valence electrons more than 4, then they are called as n-type semiconductor. Suppose we have taken silicon as pure semiconductor and for making silicon n-type we have to add impurities like phosphorus or arsenic. The impurity atoms displace some of the silicon atoms in the crystal lattice. 4 of the 5 valence electrons will generate covalent bonds and fifth will be nominally unbound and will be available as a carrier of current. The energy required to detach this fifth electron is of the order of only 0.01 electron volt for germanium and 0.05 electron volt for silicon. Impurities which have 5 valence electrons are also called as pentavalent impurities. Arsenic, antimony and phosphorus are some common examples. Such impurities have excess electrons and are therefore referred to as donor or n-type impurities. When donor impurities are added to a semiconductor, allowable energy levels are introduced a very small distance below the conduction band. Now try to understand it through energy band diagram. We have a small portion of crystal lattice in which the central atom is arsenic and all the nearby atoms are of silicon. Now, as you can see that these 4 electrons of arsenic are shared with nearby silicon atoms, but one electron is still in excess and is quite unstable. This electron is so loosely bound that even a small amount of energy is sufficient to move it in conduction band, and the energy levels for such electrons which are loosely bound is depicted by ED. And as you see, EC minus ED is very small and is of the order of about 0.01 electron volt for germanium and 0.05 electron volt for silicon. When semiconductors are doped with donor impurities, the hole concentration also decreases relative to intrinsic semiconductor. As higher number of electrons increases the rate of recombination of electrons with holes. Therefore, in an n-type semiconductor, the concentration of electrons is much greater than the concentration of holes. N in n-type represents the concentration of electrons, whereas P represents the concentration of holes. Now we come to p-type semiconductor. If a trivalent impurity such as boron, gallium or indium is added to an intrinsic semiconductor, then only 3 of the covalent bonds of silicon can be filled. The vacancy that exists in the fourth bond constitutes a hole. As we talked about the concentration of holes and electrons in the n-type, similarly we can also say that in p-type semiconductor, the concentration of holes is greater than the concentration of electrons. As you can see, the group of atoms which is shown under the p-type semiconductor in which the central atom is a trivalent impurity which, for example, taken here to be boron and the nearby atoms are of silicon. As you see that boron shares 3 of its electrons with nearby silicon atoms, but here we have a hole, and when the nearby electrons tend to move to this vacant site, then boron will become stable. However, another hole will be created from where the electron came. This procedure will keep on happening, resulting in hole current in arbitrary direction. Energy level of these electrons are represented by EA, and you can see that a very small amount of energy is required for an electron present in valence band to make transition to the energy level EA, leaving a hole in the silicon site, which ultimately results in hole current. One thing you should keep in mind that EC minus ED or EA minus EV are having approximately equal values for equal concentration of impurities, and this will eventually depend upon the concentration of impurities added to the pure semiconductor. These values are taken for moderately doped semiconductor, which are doped in the ratio of 1 part of dopant to 10 raised to the power 8 atoms of silicon. You should have a clear understanding of this topic because this topic will create base of many later lectures. We will be talking about BJT and PN junction, and in each and every device you will be constructing diagrams in which p-type and n-type semiconductors will be used, and these diagrams will come in handy. Therefore, this topic particularly should be crystal clear to you. It is quite interesting to note that the amount of impurity which must be added to have an appreciable effect on the conductivity of the parent semiconductor is quite small. For example, if a donor type impurity is added to the extent of 1 part in 10 raised to the power 8 of parent atom, then the conductivity of germanium at room temperature is multiplied by a factor of 12. On the basis of quantity of dopants, doping can be defined into 3 types: slightly doped, moderately doped, and heavily doped. Lightly doped semiconductors can be estimated to be doped with 1 part of dopant with 10 raised to the power 11 parts of the semiconductor. Highly doped semiconductor can be estimated to be doped with 1 part of dopant with 10 raised to the power 3 part of parent atom, and moderately doped concentration range lies between 10 raised to the power 6 and 10 raised to the power 8. These are also represented by different symbols. Normal P represents moderately doped, lightly doped is represented by P minus, and heavily doped is represented by P plus.